Welcome to MEI Modelling with Algorithms. We're on the topic Linear Programming 2, Simplex Method, and this is video 2.3, Application to Non-Standard Problems. So all we've seen so far is simplex applied to what we call standard linear programming problems. And of course, in reality, it may be that the problem we're dealing with can't be represented in standard form. So it'd be nice if we had a way of dealing with a situation like that. So the sort of things that could cause that to be the case are that we have a constraint that involves a greater than or equal to condition, or indeed even tighter than that, it could be we have an equality condition. It could be that in the particular situation that we're talking about, that it makes sense sometimes for a value to be negative. So we might have a condition on x it's say greater than or equal to -2, but it doesn't have to be non-negative strictly. And finally, it could be that we are dealing with a minimization problem instead of a maximization problem. So any of those things would mean that what we've seen so far wouldn't be quite good enough. So we're going to talk in this video about how we can adapt the simplex method to cope with this sort of situation. Now, in terms of what you need to be able to do as a student, you need to be able to create the initial simplex tableau if A and B are the case. And you need to be aware that we can deal with cases C and D as well, but you will not be required to carry that out yourself. So if parts of this seem a little bit too much, don't worry about it. It would be a good idea to be clear in your mind how that could work, but in terms of what's going to be required of you, that's all it is. Now, all of these things can be dealt with in the way that we're going to describe by reformulating the problem slightly from its initial formulation. So let's talk firstly about what we might do if we have greater than or equal to constraints. So the simplex method assumes that we start at the origin. Now the problem with that is that if we've got a greater than or equal to constraint, then the origin will not be inside the feasible region. And that's difficult because the whole way the simplex works is it moves around the boundary of the feasible region. So it's going to be a bit of a problem if we're not in the feasible region to start with. So what we do to get around it is we do this simplex method in two stages. So the first stage will involve moving into the feasible region, and we'll do that by minimizing the distance that we are outside of the feasible region until that is 0. Once we've done that, then we can proceed in the usual way to minimize or maximize the objective function. So here's an example then. So suppose we want to maximize 5x plus 7y subject to these constraints. So at first glance this looks very much like a standard problem that we've been dealing with, but where it becomes different is here. We've got this condition x greater than or equal to 2. And of course the problem with that is that if we were to start at the origin 0, 0, then we'd be outside of the feasible region. So we're going to explain at this point how we can reformulate this problem in order to deal with it. So in terms of the objective function itself, we're going to treat that in exactly the same way. So if you remember what we do, we take everything over to the left. So we've got p minus 5x minus 7y equals 0. And then, as well as the usual slack variables for these constraints, which we can do in the usual way, like that, and then we need to do something a bit different. So when we're dealing with this condition, because it's a greater than or equal to, we're going to be using what's called a surplus variable rather than a slack variable. So instead of having a plus s something, we're going to have a minus. So it would be minus s3. And we also need to have what's called an artificial variable, which we'll give letter A. We'll call it A1, though we're only going to have one in this case, but we could have more potentially. And that has to equal 2. So that's come from this condition. So whatever this condition is, whatever we've got, we'll subtract the slack variable and add an artificial variable. And then finally we have this new objective function, A. So we're dealing with two objective functions now, and we write this without any artificial variables. So it's going to look almost the same as the expression above it. So we've got x minus s3, but we don't have the a1, and we still have the 2 on the right. Now, the first stage then is going to be to minimize a, and once we've minimized a, then we're going to be inside the feasible region, and we can then concentrate on minimizing p. So, what do we need to do from there? Let's just tidy those equations up. We then transfer those coefficients into the simplex tableau in the usual way. But because we've got two objective functions, we've got two objective rows, and obviously two columns corresponding to objective functions. So there's quite a lot of information to put into this tableau now. And notice, because we've got this artificial a1, we've got a column for that as well. So we saw in the previous video how to transfer these coefficients into the tableau. Once we've done all that, it will look like this. And at that stage, then we're going to do the first stage, which is to deal with the objective A. So the aim is to minimize that to 0, and we can do that by using row operations in the similar way to how we maximize P. Alright. In this case, it turns out it will only take one iteration. Sometimes it may take more than that. Once we've done that, we could actually remove the columns for A and little a1, and just proceed to maximize P as we've done in previous videos. Alright, now in terms of what we would do if we had constraints that demanded equality of a variable with a number rather than just greater than or equal to, then it's quite clever the way we would deal with this. So rather than trying to find some way of ensuring that equality directly, what we do instead is include two inequalities. So if I wanted to say that x had to equal 4, I could include one constraint that says that x is less than or equal to 4. We've seen how to do that, and we've also seen now how to deal with a constraint x is greater than or equal to 4 as well. So if I include both of those, then the only possibility is that x equals 4. And then we just proceed in the usual way from there. Alright, now just to summarize this and to talk about what's going to come next, we've seen how we can do this, how we can formulate even non-standard problems using the simplex method. But what we're going to really be doing in practice now is we're going to be using technology to solve these problems. So the technology that we're going to be seeing, this bits of software that we're going to be using, will take the problem in either standard or non-standard form, and all that working that we've been doing will be done internally by the software. So as long as we can enter the problem in what we consider to be a reasonably straightforward way, the software will handle the rest of it. It's also a feature of the software, or most of the software that we're going to see, that we can restrict the variables to be integer values, and that will be handled correctly internally by the software, and that's called integer linear programming. Okay, so that concludes video 2.3, application of non-standard problems. The next video, and in fact the next 3 videos, are going to be dealing what we've just been talking about, using software, linear programming solvers to do the hard work for us.